Okay, in this video we're going to look at a change of variables for multiple integrals. So the idea here is similar to what you did in Calculus 1 or 2 when you did substitutions for integrals like this. But here the idea is that we want to substitute in variables both u and v, and both of those are going to be functions of x and y. And the idea here would be that in doing that we can either simplify the region, the function, or perhaps both. All right, so we're going to look at this theorem and this example here at the bottom. So if you look at the example, you notice that this is perhaps not impossible to integrate with respect to x and y, but it would be easier if I could somehow separate the variables. So the logical substitution here to make would be to try to see if substituting u equals 2x plus 3y and v equals x minus y simplifies the function to integrate. Our region is going to be a triangle. We have three straight lines here, so our region is going to be a triangle, which shouldn't be too difficult to integrate. So we just want to make sure that the substitutions we make don't make the region more difficult. Okay, so we're going to look at this example along with the theorem and kind of just check for these things. I stated this theorem a little bit differently than our book did, mainly just so that I could bullet point out the conditions that we need to check for using this theorem, and then we'll go ahead and actually do the integration. Okay, so first of all, it says that our function that we are integrating needs to be continuous on the region we're integrating over. So the function we're integrating is f of xy equals 2x plus 3y, that whole quantity times sine squared of the quantity x minus y. That is continuous everywhere, so that condition is okay. For these next three conditions, in order to check those, we're going to need to find the inverse substitutions. So let's scroll up here and go ahead and do that for this example. So we decided that we wanted to start by letting u equal 2x plus 3y and v equal x minus y. So those are the substitutions we're going to make. And then in order to get the inverse substitutions, I just need to turn around the inputs and outputs of those functions. So I need to have x given as a function of u and v, and y given as a function of u and v. So you just basically need to do some algebra and solve this system of equations for x and for y. So there are several different ways you can do that. I'm going to notice that I could multiply this second equation through by 3, and then I will get a new equation that eliminates y and just involves x, u, and v. So I would have u plus 3v equals 5x. And then I can solve that for x. Right, so there's one of my equations in my inverse substitutions. I now need to eliminate x so that I get an equation y in terms of u and v. So I'm going to multiply my second equation through by -2 and add that to the first equation. We will get u minus 2v equals 5y. So those are my inverse substitutions. So I will need to use those for those next three bullet points. All right, let's scroll back up and look a little bit at that next bullet point. It says the functions x of u and v and y of u and v give g a one-to-one projection of r from the xy plane to the uv plane. So this is really about looking at the geometry of our region. So we're paying attention to the region we're integrating over, and we're looking at what does that region look like in terms of u's and v's instead of in terms of x's and y's. So let's go ahead and look at that next. The first boundary is the line y equals x minus 2. The next boundary equation is y equals -2/3 x plus 2. And then we have x equals 0. So our region R is this triangle. And what we need to look at is this region that is called G that we're going to get in the UV plane in terms of U's and V's. So there are a couple of ways to do that. I'm going to make a little chart here with equations for each boundary. Our first boundary for the region R is y equals x minus 2. And what I want to do is translate that into what the boundary would be for the region G in the UV plane. So I need to get that all in terms of U's and V's. So one way to do that would be to use my equations x equals 1/5 u plus 3/5 v, put that in for x, y equals 1/5 u minus 2/5 v, put that in for y, and simplify, so that would work. This one, there is a little bit simpler way to do this particular one. You might notice that if you add 2 and subtract y from both sides, you get 2 equals x minus y, and that's helpful because if I go back up here to my original substitutions, I have x minus y is equal to v, so I can write that in terms of v. Okay, so I need a picture in the UV plane. It doesn't really matter what axis I call u and what axis I call v. I'm going to just call the horizontal axis u and the vertical axis v. So v equals 2 would be a horizontal line 2 units up on the v-axis. Okay, I'm going to use the next boundary equation and do the same thing. Again, on this one, you might notice that if you multiply through by 3 and then add 2x to both sides, you get some nice simplification. Because one of my other substitutions, I have 2x plus 3y is equal to u. So that one becomes u equals 6. Okay, for the last equation, x equals 0. I don't have those nice kind of simplifications, so I'm just going to substitute in place of x what x is equal to for the inverse substitutions. So I'll get 1/5 u plus 3/5 v equals 0. And then since I want to graph that, I might want to solve that for v, since this will be the graph of a line, and it's maybe easier to graph if I solve it for v. Okay, so the line v equals negative 1/3 u in the UV plane would be a line through the origin with slope negative 1/3. Okay, so I also have a triangle in the UV plane. This would be my region G in the UV plane. But one of the things that you might notice is that the region G is a lot bigger than the region R, and so there is a part of our calculation that will account for that. Let's go up and look at that condition on our theorem. It says the functions x equals g of u and v, y equals h of u and v give this region G, which is a 1-to-1 projection of the region R from the xy plane into the UV plane. What that means is that there are no two xy points in the region R that give the same UV point in the region G. That's what it means to be a 1-to-1 projection. So because we have linear functions that we used for our substitutions, that's not going to happen. That might happen if you had some squares or something like that in your substitutions, where you had maybe 2 input points, maybe 2 x values, a positive and a negative, and if I square them, maybe I get the same point in my region G, but we're okay on that condition for this function and this substitution. All right, the next two conditions talk about partial derivatives of g and h, and then that fourth bullet point is this 2-by-2 array of partial derivatives. That specific array has a specific name. It's called the Jacobian of the transformation. And this essentially accounts for the geometry of what happens when we transform from our region R to our region G. Okay, so let's go ahead and check those two conditions at the same time. All right, so what I've written down here is the definition of the Jacobian, and I'm going to go ahead and calculate those partial derivatives for our specific function. So I'm going to be using the inverse substitutions, where I have x given in terms of u and v and y given in terms of u and v. So my partial derivative of x with respect to u is 1/5 and x with respect to v is 3/5. Partial derivative of y with respect to u is 1/5 and partial derivative of y with respect to v is negative 2/5. And then these bars here mean determinant of a matrix. And so I not only need to find this array, but I need to find the determinant of this matrix. And that's just this product on the main diagonal minus the product on the other diagonal. We've done determinants actually when we did cross products of vectors. All right, so 1/5 times negative 2/5 minus 3/5 times 1/5. I'll get negative 2/25 minus 3/25 is negative 5/25 or negative 1/5. All right, so I will need that when I do my integration. The condition in the bullet points, let me scroll back up here, say that G and H both have continuous first partial derivatives on G. So in calculating those first partial derivatives for that matrix, I actually found them all. In this case, they were all constants, so that was met. And then it says that the determinant of that matrix has to be not 0 or is 0 at only isolated points on G. Ours was -1/5, so that is not 0. All right, so that condition is met as well. Okay, so at this point, we're ready to use the then part of our theorem to set up our integral. So we're going to do this. I'm going to go ahead and write that down below. Okay, so this is the then part of the theorem. It says this is the integral that we started with, and this part of the theorem says that that is equal to a double integral over our region G. So I'll go back up and use my picture of my region G to set that up. Here we've got our function, and I'm using those inverse substitutions to get that function to be in terms of u and v. This next part, there's something students often miss. This is the absolute value of the Jacobian, and then dA, so our differential dA. So we started with a double integral over the region R. We decided to let u equal that expression in the first parentheses and v equal the expression in the second parentheses. We went through and did all the necessary calculations and checked all of the conditions for the theorem. So it tells us that we are going to be able to set up this double integral over the region G of u times sine squared of v, that's my function f in terms of u and v, times the absolute value of the Jacobian. All right, I'm going to go ahead and pull my absolute value of -1/5, which is +1/5, outside the integral. And then I need to think about the region and the function, whether I would prefer to integrate first with respect to u or with respect to v. This function is perhaps a little easier to integrate with respect to u, but it's not hard to integrate with respect to either. So let's go look at the region. Our region is both u simple and v simple, so it really doesn't matter what order I do that integration in. I'm going to go ahead and do u on the integral for the sole reason that when I solve this equation for v, I have some fractions, and when I solve it for u, I don't have fractions. Okay, so if I go through this region in the direction of increasing u, I'm going to enter through the line u equals -3v, and I will leave through u equals 6, so I'm going to set that up. And then on the outer integral, if I collapse that back onto the v-axis, I need to look at that interval on the v-axis to think about my v limits of integration. So that means I will need to find the coordinates of the point, the uv coordinates of the point at the bottom of that. So that would be when u equals 6 intersects v equals -1/3 u. So I get the point 6, u equals 6, and v would be -2. So our v interval will go from -2 to 2. Okay, so now I'm going to go ahead and do this integration. Okay, so I've done my integration with respect to u. I got 1/2 u squared. I plugged in my limits of integration, 6 first and -3v second. I simplified that. And now I need to do this second integration. For the second integration, integration by parts is going to be what you want to do. And this is a great one for tabular integration by parts. So I'm going to go ahead and write out that tabular work and then finish this integral. Okay, so my work is over here to the side for a tabular integration by parts. I didn't use u's and v's for integration by parts like we normally would. But this first function is our function that would have been the u for integration by parts. And for this, we're going to differentiate. So I took the derivative of each of these until I got to 0. And then the second part would be what we would normally let be v. And that's what we're going to anti-differentiate. So I did use a trig identity. Sine squared of v is 1/2 times the quantity, 1 minus cosine of 2v, to make those antiderivatives a little bit easier. And so what I did at each level here was just find that antiderivative. And then for tabular method, you're multiplying across these diagonals. And you have a plus minus alternating sign that has to do with the minus sign in the integration by parts formula. So I get 1 10th times. Okay, so I've written down what I get from my integration by parts tabular method here, and now I need to evaluate this from -2 to 2. We do get some nice cancellations when we do that. Okay, so once I've plugged in my limits of integration, this whole first part here with the 36 minus 36, that will be a factor of 0 times whatever's after that, so that will drop out. Okay, on this next part, there are a couple of trig identities that might be kind of useful. Cosine is an even function, so cosine of -4 is the same thing as cosine of 4, and sine of -4 is the same thing as negative sine of 4, since sine is an odd function. Okay, so here is what we end up with at the end after I do all my simplifying. So that would be our answer in exact form. Of course, if you want a decimal approximation, you can get out your calculator and get a decimal approximation for that. All right, these problems take a while, but no one step is really difficult. It's just there's a lot of steps in doing them. So be sure you practice some. There's another example in the next video.